So today our topic is the Graham's law of effusion and diffusion. Okay. So in this video I'll be telling you about what is diffusion, effusion. Then I'll be telling you that what does this law actually states. Okay. So first of all, to understand diffusion, for example, I'm having a two container. I'm having a two container, and here I'm having the hydrogen gas. Here I'm having oxygen gas. Here I have closed these all gas. Okay. If we unlock this gas, for example, this mass is 2 gram per mole and this one is the 32 gram per mole as compared to the hydrogen, sorry. What if I unlock this? So this gas will move into this direction, this gas will move into this direction. So this is what? This is the mixing of these both gases into the different direction. That is called the effusion. Okay, so it depends upon mass and density too. Okay, so first the hydrogen gas will diffuse more, or first of all hydrogen gas will diffuse because this is having the lighter mass and this is having the higher mass. So you can say that a gas which is having lighter mass will diffuse more as compared to the heavier mass. Okay, so this was about the diffusion. Now if you're talking about, this is the what? This is a collision of intermixing of the gases. Okay, so this is what the intermixing of gases and each other in opposite direction. Now if you're talking about the effusion, so effusion means that I'm having this container and here I'm having a hole and here I'm having a vacuum and here I'm having a hydrogen gas, for example. Okay, I'm having this gas. Now if you're talking about this gas, so if you can say that I have done, you can see that here I have done the hole, or you can say orifice or flea, okay, of the gaseous molecule. So you can see that the gaseous molecule will escape here, from this, you can say that the hole. So from where the gas molecule escape from this hole is called the effusion. For example, tire, you can see the example of tire. That is what? That is example of the, you can say that effusion. Okay. So this is like happen when the, you can say that from the high pressure to the lower pressure. Okay. So this was about what? This was the effusion. Now let me give you the examples of the effusion. So the example of the effusion is the ideal gas. I have ideal effusion. Okay, ideal effusion will higher than real effusion. Okay, ideal gas will be having a more effusion and you can see the real gas will be having the lower effusion, and in diffusion the ideal will be more interacted and real gas will be, you can say that, lower interacted, because as you guys all know in ideal gas the kinetic energy is more. So this is about the diffusion and the effusion. Now let's verify this, these all are true or not. Okay, so this is the experimental verification. Experiment verification. Okay, for example, I'm having this glass tube glass tube, and here this is about 100 centimeter and this is a tube. Here I have having a one gas, this is hydrogen chloride, and this I'm having the ammonia. As you guys all know, the mass of hydrogen chloride is 40 cent, no, this one is the hydrogen having 1 mass, chlorine is having 35.5, so it's equal to 36.5 gram per mole. we're talking about the ammonia, so nitrogen having the 14 and hydrogen are 3, so they are 17. So you can say that if I have passes this two gas, which gas will move why? Which gas will be moving faster and why? The gas which will be moving faster, that will be, you can say that the ammonia, because as you guys all know, ammonia is having the less mass as compared to the hydrogen chloride. So it has covered 60 centimeter and it has covered the 40 centimeter. Okay, first the ammonia gas will be diffuse. Okay, so as you guys all know, this is the ammonia and this is a reaction which is, this is hydrogen chloride and this is ammonia. As you guys all know, nitrogen is having the lone pair like this. Nitrogen is having the you can say that the 7 electrons outer shell, so you can say 1 2 3 4 5 6 7. You can see here the lone pair is there, so we are having a lone pair of the nitrogen here. Okay, so here you can see that nitrogen is having the lone pair. Okay, so here you can see that this, when the hydrogen having a, you can say that you can say that they are want one electron, so they'll be getting from the lone pair will be of nitrogen will be getting from the for the pairing, the hydrogen will move into this nitrogen, so the reaction will occur, that will be, okay, that is the, that is what, that is ammonium chloride. Okay, so this is the acidic part, this is acidic part. Why? Because here you can see this is the weak base and this is the, you can see that strong acid. Why? Because chloride of HCl is there, so this is the acidic part, and you can say that this is the acidic salt and we are calling them as a powder, white powder. Okay, white powder, and here this is acid and this is base, as you can see that. So hydrogen is reacting with the nitrogen and this white powder is formed. So as you can see, the 60% is 60% centimeter, 60 centimeters covered by the ammonia, and because of light mass, and 40 by the hydrogen chloride. So we can say that the diffusion or the rate of density or the rate of diffusion. Okay, and as you guys all know, density is equal to mass. Okay, so the grahms law, basically grahms law state that the rate of diffusion of two gases are inversely to the square root of their densities or masses of gases. Okay, so here you can see that I want to tell you the what's the meaning of this. This means that if the mass is more, so the density is more, as you guys all know, because mass is equal to density, and if density is more, so if, density is equal to mass per volume. If density is more, volume is more. If density is more, mass is more. So this law basically exists that this Graham's law it states that the rate of diffusion is inversely proportional to the densities. Okay, so here you can say that for you can say that for gas hydrochloride, we can write here that let me write here. So we are having two gases. Okay, so we are having the rate of diffusion of ammonia directly proportional to the 1 upon density we are having of the ammonia. Okay, we have just put this formula, which is R multiplied by is directly proportional to the inversely proportional to the densities. Okay, I have just put it out the values because we are having two gas, ammonia and you can say that hydrogen chloride. Okay, after that here you can see that the proportional sign will be removed, the what will be coming, if the proportional sign will be removing, so that one, the K constant 1 upon NH3 is equal to K constant upon DNH3. Here also this will be happen the same, HCl. Now this will multiply by this, so it will become like this, R NH3 is equal to K1 density of NH3. Here NH3 is K, sorry, HCl. Okay, so we'll be dividing both to obtain what? To obtain the ratio. Okay, so here we are having the R and H3 upon R HCl is equal to K upon D NH3 upon K upon density of hydrogen chloride. Here you can see that this is a rate of diffusion, and density. Okay, so here you can see that we have, so you can write here NH3 upon R HCl is equal to K density of NH3 multiplied by the density of chloride upon K. Okay, this is right, and we have just written like this. Okay, now here K to K is cut. Now we can write here R NH3 upon R HCl is equal to D HCl on density of ammonia. Okay, here you can see that this is same, and this is multiplied, it will moving here, it will be getting divided. So this is the formula of density. This is the formula of density, because here you can see that the D is coming. If you want that the mass, so for mass we are having a formula that is R NH3 whole, the equation will be same, but at the replacement of the density will be put it out the mass of the hydrogen chloride and mass of the NH3. Here you can see that. Okay, so this is for the mass. Here you can see that higher mass. Remember one thing, the denominator value will be having the higher mass and the nominator value will be the having the less mass. Okay, so so let's do the one, you can say that the conversion to understand that how to solve the problems. Okay, number one problem we are having, that is the compare the rate of diffusion of helium and methane, okay, with the molar mass. Okay, so we are having here, we have to find what? Molar mass. So we have to put which formula? This one of the mass. So because here is no, you can say that here is no density, so we can write here that RH4, that is methane, helium, we have to find what? The mass of mass of helium. Okay, so here you can see the rate of helium, the rate of methane is equal to the what is the mass of methane. That is, you can say that the 16, this carbon 12 and hydrogen 4. So this is 16. When right here 16 and helium you are having known already, this is 4. So if you are taking the under root of this this 16, so it will be 4, and this it will be having a 2. So here you can write here that the 2 1. So we can write here that the ratio between these two gases is 2:1. So it is more clear to us that helium gas will move fast. It will you can say that helium gas will diffuse more, 2 times more than the methane, because as you guys all know, you can easily identify that if this mass is more, so it will diffuse less. If this mass is, you can say that less, so it will be diffused more, it will be diffused less. So you can identify that too. So there is no need to do the convergence, but if you want to do so, you can do by this formula. If density is there, you can find density easily by this formula. If you want to find the mass, so the mass is there for you. Okay, after that we are having a, you can say that this was the conversion of this law. So as you guys all know, this was the verification and this was the Graham's law of the diffusion and the effusion. So that was our today's topic.